So in this chapter, we want to look at a solution. We're going to start by defining what a solution is. We look at some properties of solution. We explain what the different components of solutions are. And then after we learn the properties of solution and the scientific terms for solution, we talk about concentration of solutions, and you're going to learn a couple of new formulas and terms that explain the concentration of solutions. So solutions are defined as homogeneous mixtures of one or more substances. Now each solution has two components in it, a solute and a solvent. Now the solute is the substance that being dissolved in a solvent. The other way you can distinguish between solute and solvent is that the solvent is the substance that you have more of, and solute is the substance that you have less of. Now, something to keep in mind is that a solution, when we talk about solute and solvent, it's not just about, liquid solvent and solid solute. We show you different types of solutions. So we can have solutions that are solid, liquid, gas, liquid, gas, solid, or even gas. So for example, air is a solution because air is a combination of different gases, and air appears as one uniform mixture. It's only one phase, so it's a homogeneous mixture of gases, so it's considered a solution. It's a gaseous solution, but it's still a solution. So again, remember two components of a solution, solute and solvent. It's very important for solutions for us to actually identify which substance is a solvent and which substance is the solute. So solute is the substance that you have less of, and solvent is the substance that you have more of. Now let's look at this example. Soda is a mixture of sugar in water. So which substance is the solute then? Sugar, very good, because more of the soda is just water and you just have some sugar and, caffeine and other stuff dissolved in it. So sugar is going to be the solute. Let's look at another example. A solution is prepared by adding 25 milliliters of ethyl alcohol to 75 milliliters of water. Which substance is the solvent? Water, very good. Remember, the substance that you have more of is going to be your solvent. So if you have 75 milliliters of water and 25 milliliters of ethyl alcohol, that makes ethyl alcohol to be the solute, and water is the solvent. So this is an example of a liquid-liquid solution. So this table shows you different types of solutions. So we can have a gaseous solution where your solute and solvent are both gases. An example of a gas solution could be an air. You could have a solution that's in a liquid phase, and that solution could be made of gas and liquid. So soft drinks are example of that type of solution. We can have a solution that's in a liquid phase, and it could be composed of a liquid like antifreeze, or in a liquid state we could have solutions that are composed of a solid and a liquid. You basically dissolve a solid in a liquid, so like salt water or sugar water. Now solutions are found in a solid phase too. So in a solid phase, two types of solutions you can have, either gas and solid. So an example is in hydrogen in platinum. These are the solids or compounds that are used in hydrogen fuel cells, for example. Or you can have a solution of solid and solid, which is any basically alloy could be an example of a solid-solid solution, as long as the alloy looks uniform, like in terms of the color, as long as you can tell the different metals, different phases in there, it is considered a solution. Now let's look very briefly at different properties of solutions. So again, we define solutions as homogeneous mixtures of two or more components. The ratio between solute and solvent can be varied. What's important is that we end up with a homogeneous mixture. Now, the solute could be dissolved in your solution either as a molecule, or it can break into ions to get dissolved. Solutions can either be colorless or they can be colorful, but what's most important is that solutions are clear. So if we give you a mixture and we ask you if it's a solution or not, you look at the sample. If it appears cloudy, it means that there are two distinct phases in there. It means that there are particles of solid in there, so it's not a solution. But as long as it's clear meaning transparent, meaning see-through, it is considered a solution. So you can either have a clear colorless solution, or you can have a clear blue solution, clear yellow, clear green. As long as it's clear, one uniform phase, it's called a solution. Now, in solutions, the solute doesn't precipitate out of the solvent. So even if you let it sit, undisturbed for a while, the solute doesn't separate out, and it stays as a solution and dissolved in the solvent. And the other important thing about the properties of solution is that we can separate out solute and solvent by physical means, meaning no chemical process is required to change. For example, if you have salt water or sugar water, you can easily separate out the salt and water. You can just evaporate out water, and after you evaporate out water, the salt stays on the bottom of the flask. So the salt is still the salt. The properties doesn't change, and the water that's evaporated, you can actually condense it and recover the liquid water too. So for solutions, we can separate out the solid, the two components, depending on what the components are, we can separate the two components. Now, since solutions are composed of solute and solvent, or in other terms, solute dissolves in the solvent, let's look at the solubility, see how we can find out if something, first of all, is soluble in our solvent or not. And also what becomes important is the amount of solute that's actually being dissolved in the solvent. Now, there are different ways that we can talk about this. So solubility in general, we define it as the amount of substance that will dissolve in a specific amount of solvent at a given temperature. So temperature is important, and I'll show you in the next couple of slides how temperature affects the solubility. But here is an example of how we report the solubility of something. For example, here you have 27 grams of potassium bromide in 100 grams of water at 23 degrees Celsius. So this represents the solubility of potassium bromide in water. What it says is that if you have 100 grams of water, the maximum amount of potassium bromide that you can dissolve in it at 23 degrees Celsius is 27 grams. That's the maximum amount of potassium bromide you can dissolve in water. Now, not just any water, in 100 grams of water. Now, if the temperature changes, the amount of water changes, then the amount of potassium bromide is going to change too. Now that 27 grams of potassium bromide and 100 grams of water, it's more like a ratio. So if I have, let's say, 200 grams of water, so if you have 200 grams of water, you can basically dissolve 2 times 27 grams of KBr in it, all right? So that 27 and 100 are more like a ratio at 23 degrees Celsius. Or if I have 50 grams of water, the maximum amount of potassium bromide you can dissolve in it is half that 27 amount. Now, so when we talk about solid in liquid, we talk about solubility, like if potassium bromide is soluble in water or not, or what's the solubility of potassium bromide. But when you have solutions where it's in a liquid phase, the term that we use in place of soluble, insoluble are different. So for liquid solutions, we use different terms, miscible and immiscible. So miscible is, again, for liquid solutions. That's when 2 liquids dissolve in each other. We call them miscible. And if 2 liquids don't dissolve in each other, we call it immiscible. So an example you see here on the slide is a mixture of oil and water. So oil is liquid, water is liquid too. Now when you mix these two, oil doesn't dissolve in water. So we say oil and water are immiscible. But for example, if you had water and vinegar, they dissolve in each other. So you say water and vinegar are miscible. So let's look at some solubility rules here. So this is almost like the solubility table that I have provided to you in the back of your periodic table. Again, remember that the solubility table like this one or the one that I gave you, these are very, very brief solubility tables. In actuality, we have reference books for solubility that tell you exactly the temperature and what the solubility is. So we don't have just soluble, insoluble. So in more advanced chemistry, you're going to see that we talk about partially soluble or partially insoluble. So there is a lot into solubility, but we can also, for ionic compound, just simplify it to just like soluble and insoluble to make it a little bit easier. Now look at the solubility table in the back of your periodic table, because that's what's going to be provided to you during the exam. Now try to find the solubility of barium sulfate. So very good. Barium sulfate is insoluble. And we know the rules for sulfates, that everything is soluble except for barium. Again, you're not required to memorize the solubility rules. As long as you can read the solubility table, that's enough. Let's look at another one. You want to predict the solubility of sodium chloride. Is sodium chloride soluble or insoluble in water? Soluble. It is soluble in water. Also keep in mind that in this class in general chemistry, we look at the solubility only in water. We're looking at only aqueous solutions where the solvent is water. So it doesn't mean that water is a universal solvent. Just, in general chemistry, we focus on aqueous solutions, but keep in mind that, there are other compound substances that could be used as a solvent. In fact, oftentimes in a research lab, you have a mixture of solvents depending on what you want to do. But for now, in general chemistry, lower level chemistry courses, we just look at aqueous solution. So when we ask you about the solubility, it's the solubility of the salt in water. Now, most salts are soluble in water, most of them, because salts are ionic compound and water is highly polar. That's why salts, they dissolve in water. So let's do one more example and then we move on. You want to predict the solubility of silver nitrate. And again, it's the solubility of silver nitrate in water. Is silver nitrate soluble or insoluble in water?
Soluble.
It is soluble. Very good. So most nitrates are actually soluble. How about silver hydroxide? Is silver hydroxide soluble or insoluble in water?
Insoluble.
Silver hydroxide is insoluble in water. So now let's look at some factors that affect the solubility. So temperature is one factor that affects the solubility. So solubility of solids increase with the increase in temperature. So what this diagram shows you here is that the solubility of most solids, it increases with the increase in the temperature. The reason it does is because of the kinetic energy. As the temperature increases, the kinetic energy of the solvent and solute molecules increases. So the solubility goes higher as the temperature increases. Now there is one exception here, that for gases, the solubility in fact decreases as the temperature increases. So for the solubility of solids, as the temperature increases, solubility increases too. But for gases, the solubility decreases as the temperature increases. Again, temperature goes back to the kinetic energy. So when you increase the temperature, the kinetic energy of the gas molecule increases. And remember that intermolecular forces in between gas molecules are extremely weak. So when they have high kinetic energy, they just want to escape the solution and they just don't want to stay in the solution. So you would expect the highest solubility for gases at lower temperatures. That's one of the reasons you want your soda cold. Because when it's cold, the solubility of gas, the carbon dioxide, is higher. When it's warmer, the solubility is lower. So when you open the can, at higher temperatures, all the gas is on top of the can, and as soon as you open it, all the carbonation goes. But if it's at a lower temperature, the gas is inside the liquid. So when you open your soda, it doesn't go flat as fast because the gas is actually inside the liquid rather than on top of the can, in the space on the top. So another factor that affects the solubility or may not affect the solubility is pressure. So pressure doesn't play a role in the solubility of liquids or solids. However, pressure is important for the solubility of gases. At higher pressure, the solubility of gases is higher. So for example, for soda cans, the way it works is that I believe they put the liquid in first and then they add gas to it, and under very high pressure they put gas in it because at higher pressure the gas is more soluble. And you know that it's a high pressure because as soon as you open a soda can, you hear the gas coming out, and it's just because it's under high pressure. So for solubility of solids and liquids, pressure doesn't play a role, but for gases, pressure plays a role. At higher pressures, you would expect the solubility of gases to increase. Now, since it's about solubility, let's learn different terms which describes the amount of solute that's dissolved in your solvent. So we're gonna learn three different terms: saturated, unsaturated, and supersaturated. So the amount of solute that you can dissolve in your solvent is really limited, and I showed you an example that depending on the temperature, the amount of solute you can dissolve in a specific amount of solvent is different. Now, saturated solutions are solutions that contain the maximum amount of dissolved solute in a solvent. So saturated solutions are still dynamic. There is an equilibrium in between undissolved solute and dissolved solute. Now, unsaturated solutions are those saturated that contain less than the maximum amount of possible dissolved solute in a solvent. So for example, remember for potassium boromide, we had 27 grams of potassium boromide in 100 grams of water, and I think the temperature was at 23 degrees Celsius. So if I ask you that we have a solution where you have 50 grams, 54 grams of potassium boromide in 200 grams of water at 23 degrees Celsius, do you think it's saturated or unsaturated solution? Yes, 54 grams of potassium boromide in 200 grams of water represents the maximum amount of potassium boromide that can be dissolved in 200 grams of water. So this represents a saturated solution. Now, if I have, let's say, 40 grams of potassium boromide in 200 grams of water, again, at 23 degrees Celsius, this becomes an unsaturated solution. Because we're dissolving less than the maximum amount of potassium boromide in 200 grams of water. Maximum amount we can dissolve in 200 grams of water at 23 degrees Celsius is 54 grams. Now anything less than that makes your solution to be unsaturated solution. Exactly 54 makes it a saturated solution. Now, if you dissolve more than the maximum amount of your solute in your solvent, that becomes a supersaturated solution. And this is still possible. Now, supersaturated solutions are very unstable solutions. You know, if you disturb the solution, you can cause precipitation of the solute. So now we looked at the factors that affect the solubility. Now let's look at the rate of dissolving solids. So there are a couple of factors that affect the rate of dissolving solids. One factor is the effect of particle size. So the smaller the crystals, the particles, the faster it's going to dissolve in the solvent. Another factor that affects the rate of dissolution or dissolving solids is the effect of temperature. As the temperature increases, the rate of dissolving solids increases too. And that's again because of the kinetic energy. The kinetic energy of the solvent and solute goes higher, so there is more collision in between the solid, between the solvent and solute molecules, so the rate increases. And another factor that affects the rate of dissolving solids is the effect of solute concentration. At higher concentration, the rate is higher, and at lower concentrations, the rate of dissolving becomes lower too. Another factor is the effect of agitation or stirring. So the more you stir or agitate, the higher the rate of solubility. So meaning that you can add some sodium chloride to water and let it sit. It will dissolve at some point, but if you stir it, it's gonna dissolve a lot faster. And another important is the surface area. So the more surface area of the solute that's exposed, the higher is going to be the rate of the dissolution. Now let's see why solutions are important to us. So oftentimes, in the lab when you do experiment, you use solutions. You don't use just liquids. You don't use just solids. You use solutions. You dissolve your starting material or your reactants in water and you perform the experiment. So the purpose of dissolving reactants in a solution is to allow the particles or ions to come to a closer contact. That way they would react. So for example, if you have potassium chloride in a solid form and silver nitrate in a solid form, you mix them, no reaction is going to happen. But as soon as you add water to this, potassium chloride is going to get dissolved in water, forms an aqueous solution of potassium chloride. Silver nitrate is going to dissolve in water, it's going to form an aqueous solution of silver nitrate. As soon as they dissolve in water, potassium chloride and silver nitrate, they're going to form ions. Now, as soon as you form ions, these ions are going to react with each other. They're going to a double displacement precipitation reaction, and you're going to form products. Also keep in mind that only salts that dissolve in water are going to form ions. So if you have a mixture of a salt and water, you're gonna have to check the solubility table and see if the salt is soluble in water or not. If the salt is soluble in water, an aqueous solution is gonna form and we will have ions, cations and anions. But if the salt is not soluble in water, you're just going to have a mixture and no ions is going to form. So let's focus now on the amount of solute that's going to get dissolved in solvent. That is called the concentration of your solution. Now, two terms we use for concentration qualitatively. We talk about, we say dilute solution or a concentrated solution. So dilute solution is a solution that has a very small amount of solute. Concentrated is a solution that has higher amount of a solute dissolved in the solvent. So one of the units that we use for the concentration of solutions is molarity. This capital M represents molarity, and I show you how we can find molarity. But for now, I just want you to look at the numbers here. So a 0.1 molar hydrochloric acid is a dilute hydrochloric acid solution, because 0.1 is just small number. But if I say a 12 molar hydrochloric acid, then this 12 molar hydrochloric acid is a concentrated hydrochloric acid solution. So if I'm comparing these two, a 0.1 molar is a dilute solution, and the 12 molar hydrochloric acid is a concentrated solution. So a dilute solution in a 0.1 molar hydrochloric acid, it means that I have very little hydrochloric acid dissolved in water. But in a 12 molar hydrochloric acid solution, it means that I have a lot of hydrochloric acid dissolved in water. Now, 12 molar hydrochloric acid, because it is more concentrated, meaning it has more of the solute, which is the hydrochloric acid, is going to be a stronger solution. So if you get your skin exposed to the 0.1 and 12 molar, you really feel the 12 molar burning a lot more than 0.1, because it just contains more hydrochloric acid, more solute in it. Now, this table shows the different units of concentration that we use for different solutions. Now, the ones that are important for us and we use them more for this class are going to be mass percent and also molarity. I still want you to look at the other units. So if you see them, you know what they represent, but focus on mass percent and molarity for now. And the formulas for mass percent and molarity, you gotta memorize them. So when you look at these formulas to memorize them, for example, for mass percent, that's the mass of solute over the mass of solution. This is extremely important. It's the mass of solute over the mass of solution. So when you look at concentration formulas, make sure that you know exactly if it's solute, solvent, and solution, because that makes a difference. And molarity is the moles of solute per liter of solution. Now let's look at a few examples here. You want to calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride in 150 grams of water. So mass percent, what do I know from mass percent? Mass percent is the mass of solute over the mass of solution. So we gotta identify what the solute, solvent, and solutions are. So solute is sodium chloride, and we have 50 grams of it. Solvent is water. We have 150 grams of it. Solution is the solution of sodium chloride and water, which is 200 grams. Now mass percent is the mass of solute over the mass of solution times 100. So 50 grams is our solute, 200 grams is our solution, and your sodium chloride solution is going to be a 25% sodium chloride solution. Let's look at another example. You want to know the mass of sodium carbonate needed to make 350 grams of a 12.3% aqueous solution. So what's given to us is the mass percent of the solution. It's a 12.3% solution. We also know that the mass of our solution is 350 grams. We want to know the mass of the solute here. So let's look at this. We'll start with what's given to us, which is 350 grams solution, and your solution is 12.3%. I'm going to use that as my conversion factor. So 12.3%, meaning that in each 100 gram solution, there is 12.3 grams of solute. Solute being sodium carbonate. Now grams of solution cancel out, and this gives you the mass of solute, which is 43.1 grams of sodium carbonate. So let's look at molarity. Molarity is another very, very important unit that we use for the concentration of solutions. So molarity is defined as number of moles of solute per liter of solution. So the molarity equation, you gotta memorize the formula for molarity and keep in mind that's the moles of solute and liter of solution. The common mistakes that students usually have in here is not remembering that it's liters of solution and not milliliters. So here is an example of how you can make, for example, a 1 molar potassium chloride solution. So in a chemistry lab, we usually use volumetric flasks in order to make solutions with a specific molarities. Volumetric flasks are one of the most precise glassware for making solutions, and with volumetric flasks, you can read up to 2 decimal places. Now, for this particular experiment, you're making 1 liter of potassium chloride solution. Since you're making 1 liter, you gotta use a volumetric flask that's a 1 liter volumetric flask. Now, to make a 1 molar potassium chloride solution and 1 liter of it, it means that you will need 1 mole of potassium chloride in 1 liter of the solution. Now, what is the solution? Potassium chloride and water. That's the solution. So what you do is that you calculate the mass of 1 mole of potassium chloride based on the molar mass of potassium chloride. So 1 mole potassium chloride is about 74.55 grams of potassium chloride. So in order to make a 1 molar potassium chloride solution, you measure the mass of 74.55 grams of potassium chloride, you add that to the volumetric flask, and you add enough water, and that should be DI water, until it reads 1 liter. So you mix it very well, and after you're done, you have 1 liter of 1 molar potassium chloride solution. Now, we don't necessarily have to make 1 liter of any solution. You know, depending on how much of the solution you need, you can figure out the amount of solute that you're going to need. So let's look at different examples. You want to calculate the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride in enough water to prepare a 250 milliliter solution. So we have 9.35 grams of potassium chloride, which is our solute. We have the volume of the solution, which is 250 milliliters, and we want to solve for the molarity. So to find the molarity, we need to find the moles of solute and divide that by the volume of the solution. So our solute is potassium chloride. So we have 9.35 grams of potassium chloride. In order to convert that to moles, we're gonna have to use the molar mass of potassium chloride. So each mole potassium chloride is 74.55 grams of potassium chloride. Mass and mass cancel out. So this gives you the number of moles of potassium chloride, and potassium chloride is your solute. Now to find the molarity, that's the moles of solute, which is 125 moles per liter of solution. So we have 250 milliliters. And you know that each liter is 1000 milliliters. So from here, we can find the molarity of this potassium chloride solution. Let's look at another example. How many grams of potassium hydroxide are required to prepare 600 milliliters of a 0.450 molar potassium hydroxide solution? So we have a potassium hydroxide solution. We know the volume of our solution is 600 milliliters, and we know that the solution is 0.450 molar, and you want to find the mass of potassium hydroxide, which is your solute. Remember, molarity is moles of solute, which is potassium hydroxide, per liter of the solution. So from here, I can find the moles of potassium hydroxide. So to find the moles of potassium hydroxide, you just assume a 1 here, and you do a cross multiply. So molarity times liter of solution equals to moles of potassium hydroxide. So we can find the number of moles of potassium hydroxide here. So moles of potassium hydroxide is the molarity, which is 0.45. And remember, molarity is mole per liter times the volume, which is 600 times 10 to the negative 3 liters. So liters and liters cancel out, and we end up with the number of moles of potassium hydroxide. Now, once you have the moles of potassium hydroxide, you can find the mass of potassium hydroxide by using the molar mass. So 0.270 moles of potassium hydroxide. We're going to use the molar mass of potassium hydroxide here. So each mole potassium hydroxide is 56.11 grams potassium hydroxide. So from here, we have 15.1 grams of potassium hydroxide. So the answer is D. Now let's look at some solution stoichiometry. Remember that from the molarity equation, we have the number of moles. So that's molarity is number of moles per liter of solution. And we want to show you that if we're doing reactions with solutions, how we can still do a stoichiometry, mole to mole ratio. So far, we've given you the number of molecules, atoms, ions, or we give you the mass of each reactant. But if we're dealing with solutions, we can't give you the mass. We give you the concentration, molarity of the solution, and the volume of the solution. So from molarity and volume, we can find the number of moles and look at the stoichiometry of a reaction. So let me show you an example here. You want to know how many milliliters of 0.175 molar mercury 2 nitrate are needed to precipitate 2.50 grams of potassium iodide. So let's look at the reaction. So we're looking at a reaction of mercury 2 nitrate and potassium iodide. It's a double replacement precipitation reaction. And we want to know how many milliliters of 0.175 molar mercury 2 nitrate is needed. So what's given to us is the mass of potassium iodide. So since the mass of potassium iodide is given to us, in order to look at the mole to mole ratio, we have to have the moles of potassium iodide. So from the mass of potassium iodide, we're going to find moles of potassium iodide, do a mole to mole ratio, see how many moles of mercury 2 nitrate is needed for 2.50 grams of potassium iodide. And once we have the moles of mercury 2 nitrate, we're going to find the volume of the solution. So up to here, finding the moles of mercury 2 nitrate, we've done this before. Nothing new. So we have 250 grams of potassium iodide. To convert this to moles, we're going to have to use the molar mass of potassium iodide, which is the mass of 1 potassium plus the atomic mass of 1 iodine, which is 166 grams of potassium iodide. Now, based on the balanced reaction, each 2 moles of potassium iodide reacts with 1 mole of mercury 2 nitrate. So from here, we can find the number of moles of mercury 2 nitrate that's needed to consume 2.50 grams of potassium iodide. Now, the moles of mercury 2 nitrate is given to us, and somehow from moles we have to find the volume of mercury 2 nitrate because it's a solution. So whenever you're dealing with solutions, remember the molarity equation. Remember that molarity is number of moles per liter of solution. So in order to find the volume, I can do a cross multiply here. So molarity times volume equals to number of moles. And then in order to isolate the volume, you're gonna have to divide both sides by m. And from here, you can find the volume of the solution, which is number of moles divided by the molarity. So in order to find the volume of the solution, you get the number of moles of mercury 2 nitrate divided by the molarity, which is 0.175 mole per liter. Mole and mole cancel out. So I don't have room. I'm gonna go write the final answer here. So the volume is 4.30 times 10 to the negative 2 liters. Now the question is asking for milliliters. So we found the answer in liters. In order to find the milliliters, you just gotta multiply it by 1,000. Which equals to 43 milliliters. So let's look at another example. How many grams of silver chloride will form by adding enough silver nitrate to react fully with 1,500 milliliters of 0.4 molar barium chloride solution? So we're looking at a reaction of silver nitrate and barium chloride. This is a double replacement precipitation reaction. So let's see what's given to us. You want to find the mass of silver chloride that's formed by adding enough silver nitrate to 1,500 milliliters of 0.4 molar barium chloride solution. So since I'm solving for the mass of silver chloride given the quantity of barium chloride, I have to use a stoichiometry, mole to mole ratio. So my first step should be finding the number of moles of barium chloride. So what I want to do is that based on the volume and molarity of barium chloride, I want to find moles of barium chloride. Once I find moles of barium chloride, I do mole to mole ratio. I find moles of silver chloride. And then we're going to use the molar mass of silver chloride to find the mass of silver chloride. So to find the number of moles of barium chloride, we're going to use the molarity equation. So your barium chloride is a 0.4 molar solution. And we have 1,500 milliliter. Remember that this needs to be in liters. So liter and liter cancel out. You have moles of barium chloride. Based on the balanced reaction, each mole barium chloride produces 2 moles of silver chloride. Now to find the mass of silver chloride, we have to use the molar mass of silver chloride. So each mole silver chloride is 143.32 grams of silver chloride. So moles of barium chloride cancel out, moles of silver chloride cancel out, and you end up with only mass of silver chloride. That tells us that we set this up correctly. Now let's solve. So this is going to be 172 grams of silver chloride. So that would be the mass of silver chloride that would be produced from a reaction of enough silver nitrate with 1,500 milliliters of 0.4 molar barium chloride solution based on this balanced equation. So now let's look at dilution. So dilution is a very important concept in chemistry, especially when you do experiments in the lab. You know, for your experiments, you need different solutions with different molarities. And oftentimes, you don't make each solution from scratch. You have a concentrated solution, and from concentrated or stock solution, you make the other solutions with the desired molarity. So dilution is done by adding a solvent to a concentrated solution. So basically you're adding more solvent to your solution. So the number of moles of solute doesn't change. It's just the amount of solvent that's changing, and the amount of solvent affects the total volume of the solution that you have. So keep in mind that when a solution is diluted, only the volume changes. The number of moles of solute remains constant. So the moles of solute before dilution equals to the moles of solute after the dilution. So since the number of moles of solute are not going to change before and after dilution, this is the formula we use for dilution. M1V1 equals to M2V2. So M1V1, this is before dilution. So meaning that it's the molarity and volume of the solution before dilution, or that's your concentrated stock solution. And M2V2 is the molarity and volume after dilution. And keep in mind that you can use this equation only if you're doing a dilution. So this equation is used only when you're doing dilution. So dilution meaning that from a concentrated hydrochloric acid, you go to a dilute solution of hydrochloric acid. So the type of solution, the type of solute is not changing. The only thing that's changing is the concentration, the molarity. Think about it this way. You're making coffee and you add too much sugar to it. Now it's too sweet. Let's say you add 2 packets of sugar to it and it's too sweet. What would you do to make it less sweet? You add more coffee to it. Very good. So your cup of coffee with 2 packs of sugar in it, it's your concentrated coffee because it has too much sugar in it. It's too sweet. To make it less sweet, you're gonna add more coffee to it. By adding more coffee, you're making your coffee dilute. Now, the amount of sugar that was dissolved in your coffee didn't change. There's still 2 packs of sugar in your coffee. However, you just added more coffee to it, more solvent to it. So by adding more solvent to it, your coffee now is less sweet, meaning that it's more dilute, in other words. So when you do dilution, the type of solute, the amount of solute, number of moles of solute doesn't change. You just add more solvent to it to make it more dilute. So let's look at a couple of examples. You want to know what volume of 12 molar hydrochloric acid is needed to make 500 milliliters of a 0.1 molar hydrochloric acid. So what's given to us is 12 molar hydrochloric acid, which is your concentrated solution. And from this concentrated solution, you want to make 500 milliliters, exactly 500 milliliters of 0.1 molar hydrochloric acid. So the 12 molar hydrochloric acid is your concentrated solution. And 0.1 molar hydrochloric acid is your dilute solution. How do I know? I just looked at the molarities. 12 molar is more concentrated than a 0.1 molar. Now, since the identity of my solution doesn't change during this process, I start with a hydrochloric acid solution, and I'm going to end up with hydrochloric acid solution. The only thing that's changing is the concentration, so this is a dilution process. So we can use M1V1 equals to M2V2. So we have 12 molar hydrochloric acid solution. We want to know how much of it, the volume, and we want to end up with 0.1 molar, and we want to have exactly 500 milliliters of that solution. So you could set this up, and from here isolate V1. So from here V1 equals to 0.110 molar times 500 milliliters divided by 12 molar, which is 4.2 milliliters. So what it means is that you get a volumetric flask that's a 500 milliliters volumetric flask. So you add 4.2 milliliters of 12 molar hydrochloric acid, and to this you add enough DI water until you get to this 500 milliliter line here. Once you mix them, you have 500 milliliter of hydrochloric acid solution, which is 0.1 molar. I also want to show you how you can isolate V1. If you prefer to isolate V1 first and then plug in the numbers. So to isolate V1, you're gonna have to divide both sides by M2. And from here, V1 is going to be M2 times V2 divided by M1. So this has to be M1. Now V1 still going to give you the same answer. M2 is going to be 0.1 molar. V2 is 500 milliliters divided by M1, which is a 12 molar. Now keep in mind that when you plug in your numbers, values into this equation, on both sides the units have to be the same. So if your volume on one side is milliliter, on the other side of the equation it has to be milliliters too. So let's look at this example. Calculate the molarity of a sodium hydroxide solution prepared by mixing 100 milliliters of 0.20 molar sodium hydroxide with 150 milliliters of water. So we have a concentrated solution of sodium hydroxide, which is 0.20 molar, and we have 100 milliliters of that solution. Now to that, we're adding 150 milliliters of water, which is our solvent. So we want to know what happens to the molarity of this solution. So M1 V1 equals to M2 V2. We're solving for M2. So in order to isolate M2, I'm going to divide both sides by V2. Therefore, M2 equals to M1 V1 divided by V2. So the molarity of our concentrated sodium hydroxide is 0.2 molar. We initially had 100 milliliters of that solution. And then to that 100 milliliters, we added an extra 150 milliliters of water. So our total volume now is 250 50 milliliters. So we learned general properties of solutions. In this chapter, we talked about solubilities, factors that affects the solubility, and also factors that affects the rate of solubility. We also looked at the concentrations of solution. We looked at mass percent and molarity, and we also learned how to do a stoichiometry when we're dealing with solutions. And also we learn how to do dilutions, going from a more concentrated solution to a less concentrated solution.